As the vinegar and baking soda are combined together, a chemical reaction happens. This is because of an acid-base reaction occurring between the two compounds, the vinegar acting as the acid and the baking soda acting as the base. This reaction is an example of a Bronsted-Lowry acid-base theory. The Bronsted-Lowry theory is an acid-base reaction theory which was first developed by Johannes Nicolaus Bronsted and Thomas Martin Lowry independently in 1923.
Now, before we dive into our topic, let me tell you that acids and bases are defined into three parts. We have the Arrhenius, the Bronsted-Lowry, and the Lewis. Now, the Arrhenius is the most restrictive solution as it is only applicable in an aqueous solution. In this type, Arrhenius acids release hydrogen ions in water while Arrhenius bases release hydroxide ions in water. And the second type is the Bronsted-Lowry. This type is more of a general approach. The acids are proton donors while the bases are the proton acceptors. This type applies to more reactions than Arrhenius. Lastly is the Lewis. Unlike the previous two, Lewis focuses on the electrons. Acids are an electron pair acceptors while the base are an electron pair donors.
Have you ever thought about how acids and bases work? The Bronsted-Lowry theory, which focuses on how acids and bases react by transferring protons. Acids are substances that donate protons, while bases are substances that accept protons. In simple terms, acid give and bases take. This protons transfer is the foundation of how acids and bases interact. How do acids and bases react? Now, let's look at an example to understand this better. Take hydrogen chloride, which acts as the acid, and the ammonia, which acts as the base. In the reaction, hydrogen chloride, which is the acid, plus ammonia, which is the base, yields into ammonium plus chloride ion. Hydrogen chloride donates a proton to ammonia, becoming chloride ion. Ammonia accepts the proton, turning into ammonium. This process shows how acids and bases interact by transferring protons.
Let us now understand the strength of acids and bases. So strong acids completely dissociate in water, releasing all of their hydrogen ions. And as for the weak acid, they partially dissociate in water and not all molecules release hydrogen ions. So moving on in strong bases, they fully accept protons or completely dissociate to release hydroxide ions. As for the weak bases, they partially accept protons or only partially dissociate to release hydroxide ions. So what are the acid or base strength factors? In terms of electronegativity, stronger acids have more electronegative atoms pulling the proton. This means that the more electronegative atoms the acid has, the stronger it is. And as for the bond strength, weaker bonds release protons more easily. In other words, the weaker the bond, the more it releases its proton.
Let us now proceed in pKa and pKb, two fundamental concepts in acid-base chemistry. pKa is the negative logarithm of the acid dissociation constant Ka, which measures the strength of an acid. A lower pKa value indicates a stronger acid as it dissociates more readily in solution. Similarly, pKb is the negative logarithm of the base dissociation constant Kb, which measures the strength of a base. A lower pKb values indicates a stronger base as it more readily accepts protons. There is an important relationship between pKa and pKb at 25 degrees Celsius. The sum of the pKa of an acid and the pKb of its conjugate base is always 14. This means that if you know the pKa of an acid, you can calculate the pKb of its conjugate base and vice versa. In summary, pKa reflects the strength of an acid, pKb reflects the strength of a base, and the sum of pKa and pKb equals 14.
Bronsted acids and bases play important roles in both industry and biology. In industrial process, Bronsted acids and bases are used in the production of sulfuric acid, where sulfur trioxide reacts with water to form sulfuric acid, essential for manufacturing fertilizers and chemicals. In biological systems, the regulation of pH in blood is an example of Bronsted acid-base interactions, where the carbonic dissociates into bicarbonate to help maintain homeostasis and facilitate respiration. Both in industry and biology, these acid-base reactions are essential for maintaining proper functioning and efficiency.
To sum everything up, The Bronsted-Lowry acid-base theory is a proton transfer process wherein an acid donates a hydrogen ion to the base while the base receives a hydrogen ion from the acid. When the acid donates or loses a hydrogen ion, it becomes a conjugate base, while the base that receives the hydrogen ion from the acid, it becomes a conjugate acid.